Hello, welcome to Riemann Sums and Definite Integrals. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This is Chapter 4 Integration for Calculus, Math 1411 at UTEP. We're using Larson's 11th edition calculus text this semester. But it holds for pretty much all calculus texts. 4.3 is about Riemann sums and definite integrals. More sums? Seriously? I mean, come on. We had sums all over in 4.2. In section 4.2, we focused on rectangles that all had the same width. And that was the lecture titled Area. But it isn't always the best way to go breaking up an area. Many times, it's not even possible to have same width rectangles. In order to overcome this, we need a definition that could allow the widths to be different sizes. For any selected partitioning of an interval, we're going to call it delta. All right. So, let's let f be defined on a closed interval from a to b. And let delta be a partition of AB. Now, keep in mind, a partition means we're just going to break it up somehow. So, if I'm on an interval from A to B, maybe part of them will look like this, and then we'll go a little closer, and then maybe there. So, it's not necessarily an equal width partitioning. So, any partitioning, let delta be a partition of the interval from A to B, given by A is x sub 0, and then, we're increasing. We're never going to have two lines on the same mark, up to x sub n, which is our B value. Delta x sub I is the width of the ith subinterval. So the first subinterval is so long, the second subinterval is so long, and so on. If c sub I is any point in the ith subinterval, then the sum of f of ci times delta xi from I equals 1 to n, with the ci always between the endpoints, is called a Riemann sum of the partition. So Riemann said, hey, why do we have to necessarily use left endpoints or right endpoints? Maybe I like this height for this interval, but I like this height for this interval, and this height. Who really cares where we're taking our f of x value from, as long as it's from the interval itself? So, here's a fact. The width of the largest subinterval of any partition delta is the norm of the partition, and it's denoted by the double bar, norm of delta. If every subinterval is of equal width, the partition is called regular, just like regular polygons, all the sides have equal length. A regular partition, and the norm is, of delta is delta x, which is the length of the interval, b minus a, divided by n. b minus a over n. So now we can finally define the definite integral. If f is defined on the closed interval from a to b, and the limit of Riemann sums over partitions delta given by the limit as the the norm of delta goes to 0 is the sum I equals 1 to n of f of ci delta x sub I. If that exists, then f is said to be integrable on a to b, just like if it's differentiable, right? Derivative exists. If it's integral, the integral exists. And this limit, this horrible thing to pronounce limit, is really a definite integral. So it's the sum from a to b, the length of the interval, of f of x dx, where f of x is the height, dx is the width. So I'm summing the areas from a to b of f of x dx. So this Riemann sum idea leads directly to a definite integral. This limit, as I just said, is called the definite integral of f from a to b. The number a is called the lower limit of integration, and the number b is the upper limit of integration. It's the only new forms in our integration symbols. Now, theorem 4.4. If our function is continuous, then it's integrable. Yeah, man, say that 1,000 times. That's it. If a function f is continuous on a closed interval, then we're guaranteed that the integral exists on that interval. So as long as it's continuous, I know I can find this integral. Polynomials, rational functions as long as we don't have zeros in the domain, trig functions, whole bunch of continuous functions. Now we know we can find the area under the curve above the x-axis between the values x equals a and x equals b. Another theorem, theorem 4.5, clever title, the definite integral as the area of a region. Let's see here. If f is continuous and non-negative on the closed interval, so it's always above, at the x-axis or above, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by this definite integral. So this is the area. That's exactly what we wanted. We can now find the area, much like the derivative finds the slope of a tangent line, how fast things are changing. The antiderivative finds an area. Okay, so we're going to sketch the region corresponding to each definite integral, then evaluate using a geometric formula. And here we have the antiderivative from x equals 1 to 3 of 4 dx. Now, what does this say? The function is 4, which is a y equals 4. It's a nice constant function. From x equals 1 to x equals 3, above the x-axis, I want to find this area. That's exactly what our expression says. Well, think about this. This is a rectangle, assuming I could draw straight lines, which obviously I can't all the time. That one's pretty nice, though. So the width is 2. The height is 4. 2 times 4 gives me an area of 8. This integral is equal to 8. And I found it using a geometric formula. If we're looking at the integral from 0 to 3 of x plus 2 dx, our integrand, x plus 2, is our function, y equals x plus 2. So it has a y-intercept of 2, has a slope of 1. Close enough is good enough, good representation. From 0 to 3, from x equals 0 to x equals 3, I could break this into two different pieces. Here I have a triangle. And I know it doesn't look like it, but this point is, of course, the point 3, 5. Yeah, maybe that makes it look a little bit more like it. The point 3, 5, so I know that for my triangle, my area is 1/2 base, so the base has a width of 3, times height. Well, this has a height of 2, it goes up to 5, so that's a total height of 3. 1/2, 3 times 3. Plus the area of the rectangle, which is a width of 3, height of 2, 3 times 2, area of a rectangle. 9/2 plus 6, that's 4.5 plus 6, which is 10.5. We have our area. So sometimes finding the areas of functions using definite integrals really comes down to, do you know your area formulas for other shapes? If I want to sketch the region, that is the integral from -2 to 2 of the square root of 4 minus x squared dx, what I notice is the square root of 4 minus x squared is the top half of a circle. Pretend with me that I could draw the top half of a circle. From the x value of -2 to the x value of 2, it's a circle with radius 2 centered at the origin, top half. And I know the area of a circle is 1/2 pi r squared. So I have the 1/2, I have pi. My radius is 2. Here I have the center of my circle. It goes over 2, goes up 2, goes to the left 2. So 2 squared. In my head, I was thinking ahead, I guess. 2 squared is 4. 4 times 1/2 makes 2. 2 pi is the area underneath this particular circle above the x-axis between -2 and +2. So here's some properties of definite integrals. We can find the area all day with other formulas. We're going to eventually not have to do that. We're going to put these ideas together. If a function f is defined at x equals a, then if the width of the rectangle is 0, the area is 0. So for the integral from a to a of f of x dx is 0. If f is integrable, if the integral exists on a to b, then we define the area from a to b of f of x dx to be the negative of the area from b to a of f of x dx. If f is integrable on 3 closed intervals determined by a, b, and c, then we have this additive property, right? If c is in between, even if it's not in between a and b, I could find the integral from a to c, the integral from c to b, and together it's like I went from a to b. Right? Either way, even if part of that's negative. So we have an additivity type of property here. More properties on definite integrals if f and g are integrable on the closed interval from a to b and k is a constant. Then the definite integral of k times f of x dx is k times the integral of f of x dx. Also a definite integral. It can go through sums and differences, just like all of our other functions and new things that we're learning in calculus, limits and derivatives and sums. So let's look at some examples. We're going to evaluate the integral using some values. So just given these values, the integral from 2 to 4 of x cubed dx is 60. The integral from 2 to 4 of x dx is 6. And the integral from 2 to 4 of dx is 2. If I want to know the integral from 2 to 2 of x cubed dx, I'm actually not using these at all. I'm using property 2. It's the width of a rectangle is 0. If the width is 0, the area is 0. The integral from 2 to 4 of 25 dx, I could use the constant multiple rule and throw the 25 out in front. The integral from 2 to 4 of dx is 25 times 2, right? The integral from 2 to 4 of dx is 2. So my integral is replaced by 2. 25 times 2 is 50. Once again, if I still know my values here, the integral from 2 to 4 of x cubed plus 4 dx can be written as the integral of x cubed dx from 2 to 4 plus 4 times the integral from 2 to 4 of dx. Well, I know in green here, this integral is equal to 60 plus my constant 4. And the integral here in blue is 2. So that's 60 plus 4 times 2, which is 68. And then we could even go crazy and find the integral from 2 to 4 of 10 plus 4x minus 3x cubed dx. We look at it as 10 times the integral from 2 to 4 dx, which is 10 times 2, plus 4 times the integral from 2 to 4 of x dx. Right, that was our 4x. X dx is 6, so that's 4 times 6. Minus 3 times the integral from 2 to 4 of x cubed dx, and I know that value is 60. So I have 20 plus 24 minus 180 should be a negative 136. So using the constant multiple rules and using the sum and difference rules, we can take this polynomial and break it down into its pieces in order to find the antiderivative or the definite integral. If we're given the integral from 0 to 5 of f of x dx is 10, and the integral from 5 to 7 of f of x dx is 3, whatever this function is, that's all we know. If I want to find the integral from 0 to 7, well, the integral from 0 to 7 of f of x dx is the integral from 0 to 5 of f of x dx plus the integral from 5 to 7. Right, 0 to 5, and then 5 to 7, add them together, and we'll get 10 plus 3 for a total area of 13. And if I want the integral from 5 to 0 of f of x dx, and I don't do this very often. I almost always, if I have an interval, I put it in what I consider to be the correct order. A lower limit is a number smaller than the upper limit. However, this arrives sometimes in calculations that we have to do. We're going to see it in substitution a little bit later in chapter 4. And so sometimes this happens, and you need to be able to straighten it out and correct it in your head, if nowhere else. The integral from 5 to 0 of f of x dx is the same as the integral that makes my heart happy from 0 to 5 of f of x dx. So it's negative 10. So this, it hurts my heart. 0 to 5 makes it much better. I only have to offset it by a negative sign. Well, that's it for Riemann sums and definite integrals. Thank you for listening.